Good afternoon to all of you. In the last class, we learnt a few circuits, arithmetic circuits, mainly various kind of adders. And today, what we are going to see is basically we are going to focus on multipliers. Okay. So if you see normal multiplication, binary multiplication, how it's done. You have 1 0 1 0 1 0, which is a multiplicand, which is being multiplied by a multiplier, which is 1 0 1 1. Like we do decimal multiplication, same is the case with a binary. So you multiply 1 with 0, you get 0, 1 with 1, 1, 1 with 0, 0, again 1 with 1, 1, 1, 0, 1, you get it, right? And then you take the next significant bit and then you shift it towards the left and then you write it here, right? So, but in binary things are slightly more simpler than the decimal. So what is this actually? What is this operation? If you can see, anybody can tell me what is this operation? 1 into 0 is 0, 1 into 1 is 1. So this is a simple AND operation, right? So these are known as partial products. Okay, partial product means you just take one bit from the multiplier and you create a product. Okay, so this is one product. This is second partial product. Third and fourth. So for a 4-bit, you have generated 4 partial products, and as you move from the LSB towards the MSB, the partial product also needs to be moved away from the LSB by 1 bit. Okay, so and then you add it. So this is what a normal binary multiplication is all about, right? So the same thing, if I have to implement in a hardware, so this is what a hardware looks like, right? So now if you see here, this is like A0, A1, A2, A3, A4. So I have just written and I have drawn an example for 4-bit into 4-bit addition, where let me take a pen and then what I'm multiplying is an A0, okay, A1, A2, A3 with B0, B1, B2 and B3. Okay, so this is a 4-bit number, this is a 4-bit number. Then I am going to multiply it. So these are what are these? These are the result of the AND operation. Okay, so these terms we get by using AND gates. So those AND gates are not shown out here, just for so that the slide is not cluttered, but otherwise each of this will be generated by using an AND gate. Okay, so these are all so once these small outputs of the AND gates, and they are all available simultaneously, because all these 8-bit information, 4-bit of multiplicand and multiplier 4-bit are available. In one go, you can use a lot of AND gates and get all these AND results of the AND in one go. Okay, so all these are available after one gate delay. So everything is available. Then after that, how to do this summation of all these things, that is shown here. So you see here A0, B0, that comes directly as the product. Okay, so since if you see here, this 0 directly comes here. And then you need to add these two, and then you need to add these things. So same thing is done here. So A0, B0 is straight away brought as P0, which is known as the product 0, and that the least significant bit of the product. The next significant bit of the product, you need to add these two out here, right? So they have been added. Now since there is no carry which is expected, because this is directly coming down, there is no carry here. So I might as well use just an half adder out here, add these two and get here. Now there will be one carry generated from this stage that needs to be taken to the next stage. So the carry which is coming here needs to be brought out here. So I have these two, okay, and then I have the carry. So I use a full adder. Again I have this one which is remaining here. So I have the sum coming from here and this one bit which is remaining here. So I need to add that. So I can use an half adder. So I do an half adder and get. Now in the next stage, now obviously I have 1, 2, 3, 4, and also a carry which is coming and from this stage. Okay, and I have used one full adder and a half adder here. So there could be a carry here or here also. So it doesn't matter. All those carries needs to be catered in this stage. But obviously we have an bare building block is a full adder where it can maximum have 3 bits. So you can't do addition of so many things in one go. So I have just one full adder which takes care of a 3 set of inputs, one carry from here and the two new things which is there available here, and then again full adder where this A2 is again taken care, A2 B1 is taken care of, and the sum which is coming from here and the carry which is taken here. Again I use one more full adder where this remaining one bit output of the AND gate that is taken care out here, and the sum which is coming from the top is taken care of here, right? And all these full adders or half adders, they also generate carry. So that will be taken care of in the next stage. So next stage again you have these three. So they have been taken care of here, and then this obviously these carries also have been taken care of here. So I have used an half adder here. You can use a full adder also here and shift this to the top. You can do that also. Doesn't matter, but it's all the same. Not going to make much difference. So you can arrange this. So and finally you come here. So now in the final thing, you see this product 4 into 4. You get an output which is of 8 bit. Okay, from P0 to P7. So from the final full adder, this is the carry and this is the sum. So this is the sum and this is the carry for them. Otherwise, these are all the sum. Okay, these are all the sum. Only the final carry needs to come out here. So this final carry is coming here. So this is known as an array multiplier. So this is the simplest of all the multipliers, but it has got its own disadvantages. Okay, we try to find out what is the disadvantages. First of all, trying to find out what is the total hardware requirement. So if I just consider all of them as full adder, full adder, full adder. So this is an 4-bit adder. So how many 4-bit adders are required? One 4-bit adder, right? Second 4-bit adder, third 4-bit adder. That means 3 4-bit adders are required, and this was an example for a 4 into 4 multiplication. So that means I actually require m into n bit. Okay. So you require n minus 1 m bit adders. Okay, so this n bit adder, this is a single word, that is 4-bit adder. How many of them we require? N minus 1. So in this case it is 4 minus 1 4-bit adder, that is 3 4-bit adders are required in this particular case. In general, if we are doing an n into m multiplication, then I require n minus 1 of m bit adders. Okay, so that is a generalized formula for that, right? And then also you require m into n AND gates, because all those AND gates are not shown here. So A1, B3, A2, B2, all these are all AND gates. So these AND gates also will be required. So you will require m into n AND gates also. So this is the total hardware requirement. With respect to the delay, now if I come to the delay aspect, so you will see here, this has got multiple paths, actually critical paths, last path. Okay, so here you have what is shown in red. Okay, this is one path. What is shown in green here, one red and then green here again this. So it has got multiple paths. So the worst case delay will be defined by so all these horizontal ones are carries. Okay, so how many carries are required? If here it is 1, 2, 3, 4, 5 carries. So the total number of carry delay which will be there in this particular array multiplier will be m minus 1 plus n minus 2. So for in this particular example, we have used an 4 into 4 multiplication. So 4 minus 1 will be 3, and n minus 4 minus this is so 5. So if you see here 1, 2, 3, 4, 5, all these horizontal are carry. So 5 carry delays, and some delays are, these are all sum inputs which are coming, vertical ones. So I have a 1, 2 and 3 out here, right? I am not taking this carry because I am assuming that some will have more delay than the carry. Okay, so that is why there are 3 carry delays. So n minus 1, so 4 minus 1, 3. So 3 sum delays and so now it is not m into n AND gate delays, just one single AND gate delay, because all these things will be generated at the same time parallelly. So there is only a single AND delay. Okay, so this once A0 B0 gets generated, all of the other things also get generated. So in the critical path there is only one AND gate delay. Okay, so that one AND gate delay. So this is the total delay. So so just to now if you have to optimize the delay, there is no way, because all these blocks, each of these blocks will have to be optimized for speed. If you start doing that, obviously you will end up making complicated adders and more area, because we have seen fast adders are there, but that they come along with a cost of penalty. There will be penalty of area and power, right? So here each and every block is critical, because everything comes in a critical path. So there is a better option which is known as carry save multiplier, right? Okay, is it okay till here, everybody? Anybody has got any doubt? Yeah, Sahu, Sridhar, anybody? No?
Sir,
No,
the
sir.
half adder it should be 4 or 3, sir. The top row has one more half adder.
Here? No, did I mention anywhere? I am just telling here. Okay, a generalized equation is an m bit adder. So this everything I consider as an full adder. One 4-bit adder.
Okay.
This is one 4-bit adder. So m bit adders. Is that okay?
Okay, sir.
Right? Okay. So now I have something known as a carry save multiplier. Here what we are doing is we are not propagating carry within the same stage. Okay, here horizontally there is no, the carry is propagated into the next stage, and that is why we call it as carry save. Carry save means we are saving the carry for the next stage to compute. We are not propagating. So this half adder, they all work parallelly. They are not waiting for any inputs from the same level. Similarly, all these in a full adder or one half adder which we have used, okay, so they are waiting from inputs from the previous stage, but there is no carry which is required to be propagated horizontally out here. So we are saving that carry for the next stage. So here, so this is again I have not written all these things, this A1 B3 out here, but they can be written out here also, right? Same thing, everything can be written here. So obviously here the advantage of this particular carry save multiplier over the previous one is there is only one critical path. Okay, this is the critical path, or this is not the critical path, right? This is because this is a shorter path. This is the longest path. Okay, so the critical path is now here and then here, right? So what I can do is I can use these as a normal low speed adder, ripple carry adder, whatever I have, right? I can just concentrate on these three elements, and also I can use like carry look ahead adders and all we saw, right? So I can so this entire 4-bit adder I can use a fast adder out here. So I don't have to optimize every particular block out here, right? So that is the advantage. But the disadvantage out here is, okay, one additional row of adders will be required. Here 1, 2, 3, 4 rows of adders are required. Here only 3 are required, right? So obviously one additional row of adder is there. Okay, but the total delay can be optimized by instead of using a ripple carry out, you can use slow adders out here and a fast adder here. So overall you can get a better speed, okay, while consuming lesser power out here as compared to the previous. Here if you want to achieve the same speed, every block needs to be optimized. Okay, so here that is not the requirement. Only the last stage requires to be optimized. So if I try to compute the total delay in this particular case is T and, okay, because all these arrows, here input arrows indicate these products, right? So that means there is an AND gate there, plus one half adder, full adder, half adder, it is written here. So what is coming like this? These are all carries actually, which is shown at 45-degree angle, right? So 1 carry, 2 carry, 3 carry. So n minus 1 carry. Okay, so that carries are required, and this is T merge. Okay, T merge is the total delay combined of this whole block. Okay, so you can use an fast adder in this particular block instead of a ripple carry adder. Okay, so that is the reason it is written as T merge. Okay, mind you, this is not the single carry delay or a single sum delay. This is the total delay of this particular whole block. Okay, so is it okay till here? Okay, so the disadvantage is one additional this row is required here. Okay. Now, if you see here, till now we are talking about full adders. While we spoke about full adders and all in the normal adder blocks, okay, we try to optimize the carry. Okay, but in multiplications, now if you see here, okay, the sum is also equally critical, right here. So I don't want to generate first carry and then use to generate its sum, because these kind of in multiplication, all these full adder blocks, the sum and the carry both have an equal importance. Okay, unlike a normal carry, n-bit carry, where carry has got more importance. So that's why we use a transmission gate XOR and then use this XOR to generate the sum and carry. So this is a transmission gate XOR. Did we discuss this in the last class? I think so, right? Have we discussed this? Anybody? Okay. If you don't remember, let's. Yeah. If
the implementation we had discussed.
Okay. So this is a transmission gate as well. And did we discuss this? No? Okay. So this is a full adder with transmission gate. You can make a sum and a carry here. What is done is this is A bar and this is C bar. Now this is a transmission gate, which is shown here. Okay, only thing is it is shown, it is drawn the other way around here, where inverter is shown towards the right and the transmission gate is shown towards the inside. Okay, here if I go back, this is just a mirror image out here at the top, and same is drawn here. So I am giving one input as A and B, one input as B and the other input as A. If you see here, same circuit, A is being given from here, B is given from the top and bottom. Now, same thing is done here. Now A and B are being given, so you get the XOR. A XOR B is propagation, right? So A XOR B is propagation. So I am getting propagation. Also, what I am generating is I am generating propagation bar. Okay, what is propagation bar? Propagation bar is inverse of that, right? P. So what I need to do out here, I just have to change the signals which is being given to the propagation to the transmission gate. Okay, now here A is being given to the NMOS. Here A bar was being given to the NMOS, and A was given to the PMOS. Here A bar is being given to the PMOS. So by this structure, I am generating P and P bar. Once the P and P bar is generated, okay, propagation and propagation bar, then I can use this particular structure to generate the sum and the carry signals. Okay, so let's try and analyze how this is working. So let's
Sir, can you change the pointer, please?
Yeah, sure. Yeah, let me use the pointer now. I would want to write a few things. Okay, now this is a propagation, right? So let us take a condition of propagation is equal to 0. Okay, if propagation is equal to 0, for what happens in the sum? If propagation is equal to 0, So the top gate will be enabled and the bottom gate will be disabled. Correct? What is propagation? A XOR B from this gate. This is an XOR gate. So propagation is 0. Now if carry is 0, right? If carry is 0, I'll get this 0 coming here, right? Propagation is 0. Carry is 0 means, okay, sorry. Carry is 0 means this carry bar will be 1 here. So I will get a 1 here, I will get a 0 here. So obviously if propagation is 0, that is an and also the carry in is also 0, then I will get sum is equal to 0. So that satisfies my condition. Now suppose carry is 1, okay, then this becomes 0. In that case this is 0 and this will become 1 again. So that condition is satisfied. Now the other condition is propagation is 1. Okay, in that case this top gate. So let me clear this. The propagation is 1, right? In that this bottom gate will be enabled. Propagation is 1. Now what happens? Now if the carry is 1, propagation is 1, carry is 1. Okay, that means there are 2 ones actually, right? In that if there is 2 ones, then the sum has to be 0. So now you see here this 1 will come here and this is the inverter, so sum will go to 0. Okay. The other condition for an propagation to be 1 is either it is 1 0 or 1 0, that is only 1 1 is available here, right? So in that case P and C in is 1, so 1 plus 1, if C in is 0, then what happens? This is 1, then 0 will come here, it is going to be 1 here. So this is going to generate an sum. Okay. So this is not a transmission gate. Okay. This is not an XOR gate or something. It is just pure transmission gate. This is the XOR gate is used only to generate propagation and propagation bar. Now if you consider for the carry how it is done. Now let's take a case where propagation is 0. So propagation is 0. So the top gate will be enabled in that case, right? Because this is the propagation signal. It is being given to the top gate will be enabled here, right? So and then now A is 0. So if propagation is 0, okay, that means either it is a 1 1 or a 0 0. Again, one more condition I am telling, A is suppose A is 0, then this will be 1 here. So A is 0 means it is 0 0 condition only, right? So A is 1 out here. So in that case, will carry will be generated? It should not be generated because, right, propagation is 0 and A is also 0, right? So that means it is both are B is also 0. So in that case, carry will not be generated. So A bar is 1 here. So I'll get 1 here. It will go to as a 0. Okay, straightforward. Now suppose propagation is 0 and A is 1. Okay, what does it mean? Propagation is 0 means it is these two conditions, 1 1 or 0 0, and A is also 1. So that is why this is 0. So it has to be 1 1 condition only. So carry has to be generated. So I have a 1 here, I have a 0 here. This will go to a 1 here in that particular condition, right? Similarly, if I talk about propagation being 1 here, in that case this gate will be enabled, right? Propagation is 1 here. So what is the propagation 1 condition? It is either 0 1 or 1 0, right? Or 1 0, sorry. In that case, what is to be done? C is to be propagated as it is. So C bar is coming here, again one more inverter is there, right? So that means C will come out here, C in will come straight away here. So that way this is generating sum and sum bar. So in multiplier designs, okay, so instead of having a 28 transistor and things like that, so this is a better option. The better option because one, it has lesser number of transistors. Second, both equal importance is given to sum and carry. Okay, so they come out together because sum is also equally important for multipliers. So this is the kind of circuits which are generally used for implementing full adders in multiplier cells. Okay, because we see these multiplier cells, all these full adders are there. So this is the kind of circuits which are used. Okay. okay, within the multiplier cells for implementation of full adders. Okay. Okay. Now this kind of structure will also required, right? So all are these like A3, A2, A1, A0, B0, B1. So this entire structure is also required, right? Because n into m adder. So all these arrows which we have shown, I have not shown here. Okay, all these AND gates. Okay, so just to not to clutter the presentation. Otherwise, all these AND gates, these many AND gates also will be required. Now you have so many products, right? These are all known as the product terms which are generated. Okay. Now these are the right AND gates. Now you have to add these two, right? So one way we learnt about various methods of doing it. This is one option. This is second option. So what Wallace tree does is, okay, Wallace tree, okay, it tries to optimize the number of full adders and half adders and the delays associated. Okay, so the first step in doing that is to rearrange this like this, right? Are we doing any manipulation of data? Nothing, right? It is just the way it is represented here, right? Z0, Z0, Z00, 01, 0, this is again, these are 3 here, these are 4 here, these 3, these 2, these 2, right? It is just the way we are drawing it on paper. Okay, that is slightly different. Rather than writing it like this, we are writing it, just drawing it like this, just to visualize whether we can do some kind of optimization with respect to a number of gates that are full adders and half adders that are required. Okay. Now there are certain set of rules, okay, for further optimization. Okay. So first is this. This table, you see what is this table? Okay, these are the terms which are being multiplied. Okay, you are multiplying this, you are getting P00, you are doing this. So this structure, okay, I have written it like this. Okay, so I have used some kind of naming methodology which may not be very logical, right? But I have why is this showing as 2 9? I think I made some mistake. 0 0 0 1 0 2 0 3 1 0 1 1 1 2 2 2, right? 2 0 2 1 2 2 2 3 3 0 3 1 3 2.
329 is I think written.
1 2 3. Yeah.
There is no 9. 0 to 3 0 to 3.
Yeah, yeah. I drew it in an Excel sheet and then I took a snapshot. So I am not able to remove this now as of now. Okay. So this is probably not there. Okay. This is not there in fact. So let me just put a cross mark. I will update this. I think I have that Excel sheet still with me. So I'll update this picture. Okay. So this is not there. So I have just returned this product. Now the rule which was suggested by Wallace. Okay, this is the name of the person who suggested this particular method of optimizing the number of half adders and full adders. He says use full adder and half adder to reduce the column height. So this is the column height, right? This is 4 out here to reduce the column height. Now, however, it says to use an half adder or full adder, previous should have 3 or more partial products. Okay, to use an half adder, actually to use a full adder, again this half adder is not there. To use a full adder, previous column should have 3 or more partial products, and to use an half adder, previous column should have 2 or more partial products. Okay, so this is the second condition which he imposed. And stop when 2 bits are available in particular column. Okay, because finally we are going to use a fast adder. So we will keep optimizing it till we get only 2 rows. Okay. okay, in each of the column. So if you see, this is the step 1. Now if I see here, before this there is obviously there is nothing, so I leave it as it is. So this comes as it is in the bottom. Here there are 2, right, but I am not going to use an half adder, because preceding this there is no half adder requirement. So I am going to put this as it is in the bottom, right. Here I have 3. I could have used a full adder, but the condition for full adder is previous to this there has to be at least 3, but there are only 2. So that is the reason I am using only a half adder. So I have tried to do put some colors out here. So I have put an yellow fill out here. So I am going to replace these 2 by an half adder, okay. And now here there are 1, 2, 3, 4, and previously there are 3. So I can use an the condition is for a full adder, previously there has to be 3. So I have used an full adder here. Here also there are 3, and previously there are 3. I have used a full adder out here, right. And this, there is one more condition, the last condition, stop if there are only 2 items are available. So here only 2 is available, right. So that's why I am not going to use any adder out here. There is 1 here, so I am leaving at this. So how I have come from step 1 to step 2, is it clear to all of you?
Yes.
Yeah, okay. So this is now representing. Now these 2, okay, I am calling it as just S1, okay, the first. So I am writing S1 there, because now that is the sum 1, and that will generate a carry also. So that carry I have taken it to the next column out here, okay. So these 2 yellow, this has come like this now. Is it okay?
Sir,
Yes.
can you please repeat that point?
Which point?
How you combine those 2?
These 2.
The P02.
Yeah, these are this is 1 bit information. This is 1 bit information. If I am going to put an a half adder out here, that will give me 1 sum and 1 carry,
Okay.
isn't it? So that sum
Okay.
I am putting it here, carry I am putting it here.
Sorry, can you please change your pointer? It's
Yeah,
not
again,
visible.
because I am writing in between also, that is the reason. Okay, size has gone. Yeah, is this okay with all of you? S1 and C1, where it has come from? What it has done? It has compressed this 3 into 2 now, and taken the
Yes, sir.
carry to the next stage. Is it okay with all of you? Yeah, Kalyani,
Yes,
is
sir.
it okay?
Yes, sir.
Okay. Now I have put a full adder out here. Okay. When we see the hardware, it will still become clear. Now we just try to concentrate it only how these boxes are getting transformed. Okay. Then we will correlate it with the hardware. Then it will become very clear. Okay. Now this I am replacing it with a full adder. So it will generate 1 sum and carry. So that sum I have put it in green out here, and carry is I have taken it to the next stage. Okay. So this is the second adder block. Okay, that is why I have given this is the first, although it is a half adder, I have named it as 1 1. This is the second adder block, which is a full adder. So sum is coming here, carry is coming here. This is the third adder block which I am using. So sum is put here, carry is put here, right? Is it okay till here?
So it's
Now-
a carry save kind of.
Pardon?
It's a carry save kind of.
Yeah, carry is being
Approach.
taken to the next stage. Yeah, it is exactly like carry save. Now, if you see here, this was on a 4 row out here. Now it has come to 3 row out here, right? So now let's see further try to optimize it. What we do now. This is the second step. This we I have repeated from the second. Now here let's see whether I can do something out here. So this is a single bit. So I don't do anything about it. This is again 2 bits, so I don't do anything. I have to add these 2 also. So I don't do anything about these two. Here I have 3, but preceding this I have just 2. Okay, so the condition for a full adder is the preceding also should be 3, right? So, but because there is only, so I put only 2 half adders out here. Okay, so I am putting half adder out here. So I am going to put a half adder out here. So I have just put an yellow band out here. I am going to put an half adder subsequently. Here also there are only 2 are available. Preceding also there are 3 available, but there since only 2 I am going to put an half adder out here, right? And here I am going to use a full adder out here. Okay, because if you see here, there is a carry which is going to come here. Okay, so it will be 3 actually. So because I am going to put a half adder, there is going to be a carry which is going to come here. So that is the reason I have put a full adder out here. Is it okay? Because I have just split this into 2, but you have to see that whether there is a carry going to come here. There is going to be a carry which is going to come here. Okay, from here. So that is the reason I have taken, I have considered this as 3 and put a full adder here. So now if I try to map this, so initially I used 3, 2 full adders and 1 half adder. Now the 4th half adder is going to come here. So I put S4 here and the carry is going to come here in the next. Okay. Now S3 and C2 are going to become S5 here and C5 is going to come into the next stage. Now this is a full adder. So S6 and C6 is going to come here. So now I have this kind of block which is coming here. Is it okay? How this block has come?
So after every stage, we are recursively applying the algorithm.
Correct. We are using the same algorithm at every step. Now the ultimate aim is to get. Pardon?
Yeah, and how do we visualize it as a hardware? Because it will be every clock tick, or
so this is what the hardware looks like. Okay. In the first stage, we have 2 full adders. These are all the partial products. Okay. These are the 2 full adders and a half adder. Okay. In the next stage, this is the first stage. So 2 full adder and a half adder. Second stage, I have 1 full adder and 2 half adder, 1 full adder and 2 half adder. And finally, if you see this, okay, so this I have a fast adder here, 6-bit. Now this is just a 6-bit fast adder which I am putting out here. Is it okay with all of you?
Yeah, got it.
Right?
Can you please go to previous slide?
Yeah.
Step number 3. Why didn't we put here full adder S2, P30 and C1?
Where?
That I didn't.
Here.
Yeah, there.
Here. Because the
Yes.
previous, the condition is the previous there has to be an 3. Okay. Here also this is 2. So this, see now if you understand this, why are we leaving aside these 2? Because ultimately we are going to use a fast adder which can take care of 2 inputs. Okay. So that is why wherever there are 2, we are leaving as it is. Okay. So here also there is only a 2. Okay. But one right, there are only 2. So wherever there are, this is going to be, if I use a full adder, okay, now so that will combine and that will combine this also, but I require 2 inputs finally. So I just combine these 2. Is it okay? So the rule is, if you see in the previous stage, if there are 3, only then I use a full adder. Here I am using because there is going to be a carry which is going to come here. I can foresee that there is 1 carry. So there will be 3 here. But here this is not going to generate. This carry actually which will be generated here, that is being taken care of by this full adder. Okay. So similarly, so that is the reason in this particular I am using full adder, because I can foresee there is a half adder here that is going to come push 1 carry here. Okay. So that is the reason, only reason I am using full adder here. So this is how.
And the fast adder is full adder, or
this. See, this could be a carry look ahead adder. Instead of ripple carry adder, we learnt about full adders, right? Various. This could be all ripple carry. This simple block. This could be an carry look ahead adder also.
So internally it is a full adder.
Fastest. Yeah, internally full adder. This entire block could be a fast adder, right? So this is known as Wallace tree
I
multiplication.
think we need to simulate this so that we understand it correctly.
Yeah.
Maybe
Okay.
after the class. Yeah.
Okay. We can try
Sir,
that.
can you just show the previous slide once more?
Yeah.
Sir, here in step 3, in that S3C2, there also in the previous stage there is a half adder, right? So there
Correct.
can be a carry coming in, no? So we can put a full adder there, right?
Where? Here?
In that S3C2, yes. Previous stage is a half adder. So that can generate a carry, right? So there shouldn't we put a full adder?
No, but ultimately you require 2 bits as a balance out here, because you are going to finally put a full adder in the bottom here. You don't want to underutilize this fast adder, right? So that is the
so
reason.
always 2 bits should remain.
2 bits should remain. So if I use, then I'll have to give one input as 0 in that particular case in this fast adder. So that you have to take care that you don't land up in that situation. Okay, so that is the reason. Okay, so this is what we done. So this is probably there in your textbook. Okay, here what they have done is, but this doesn't hold good for a big circuit. Here they have just taken these 2 inputs. There are 2 inputs. They have put in a fast adder, full adder, full adder, full adder, and then after that, whatever is the remaining bits, they have taken it as half adder, half adder. So this is what what they have done is, you have a first bit coming. This is a fast adder. First bit, there are 2. First bit as it is they have taken. This they have taken here. This they have taken it here. This they have taken to the next stage. Then they have used a full adder here. So this kind of a schematic you cannot logically build. Okay, so if you see come across this in your textbook, probably you can use this algorithm, which is better explained in this book, right? Karim Abbas. Okay, so you can use this book where he has given some examples. So we'll see the for a 4 into 4 multiplier how it is done here. So I think
can you please go to that fast adder slide? One more, that blue one. Yeah, 6 bit 1, 2, 3, 4, 5, 6, 7. Okay, it's a 6 bit adder, no?
Yeah,
7 blocks.
No, this is the outputs. Here, from here, you will get the carry and the sum from the MSB. Right? This will give sum, this will give sum. This final will give sum and carry, like for a 6 bit adder, fast adder.
No, but there should be only 6 bits, no?
No, there will be total 7. This will be sum as well as carry. Total 4 into 4 will give 8 bits, right?
Yeah, that I understand.
3, 4, 5, 6, and 7. What's the question like?
No, this is 6 bit fast adder.
Yes.
So it should be Z5 down to Z0. And 1 carry. It will come from the Z5 block.
1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. This is just a wire. Yeah, like somebody said. This is Z0 is just coming. Simple wire. From here to here is an adder. 6 bit adder.
Okay.
This one is just taking out as it is. Okay. So this. Okay. Like here it is shown here. Okay. It's just coming straight. Now this is what is done for a 4 into 4 multiplication. You see here. Okay. This we are going to. This is instead of writing these boxes. So in this you make a half adder box here, full adder box here, a full adder box here. Right. These two are getting combined here. So this is getting two combined out here, and then one carry is generated, that is put out here. Now there were 3 here. Okay, so now one was already left out here, one is carry, so total 3 out here. Now I am combining, I am using only a half adder here. What we did in the previous slide, same thing is being shown in this figure out here, right? And this 3 is now become only 2 dots out here, right? Because I have compressed it by using a full adder, so 2 out here. So this will give me only 1, but 1 carry is going to come from here, so that carry. Now I am combining that carry which was generated, and I am putting one more box here. Now here from here 1 carry will be generated. Now there were 2 earlier here, now 3. Now all the 3 are being combined here from here to here. So this is what we did here. Same thing is been represented as dots out here. So why I am duplicating this out here? For the next multiplier, we'll see. So this I drew for your comprehension, but otherwise in the textbook, this is the way it has been explained. Okay, so you can see for how it is being done for 5 into 5 also. So here the first I have these 2 are being combined because already there is 2 out here. So that is why this is being combined. Here I am putting a full adder because already there is a 3 here. So here also I am putting 3 because already there is a 3 here, 3 here, 3 here. Here I am not going to put because minimum 2 has to be there, right? So that is the reason I am putting here. Now this is 5 into 5 multiplier. Okay. Now so this gets transformed like this. Okay. So some amount of compression has happened here. Now further I want to compress out here. Okay. So now if I have to compress out here, so these 2, this has become a dot here, this has become a, these have gone, these 2 have become a dot here, and 1 carry is going to come here. These 3 sum is going to remain here. So one dot is there, 1 was previously available here, and 1 carry from here is going to come here. Now there is 3 here, but previous stage there is only 2. So I am putting in one more half adder here, not a full adder. Here also, if you see here, 1 half adder is put here and 1 full adder is put here, right? Because there were 5 out here. So this gets combined into a single dot. This also gets combined into a single dot, and 1 which is coming from here. So there are 3 here, and from here as well as here, 1 carry is coming to the next stage. So earlier 1 was available here. These 3 has got combined into 1 dot and 1 carry to the next stage. So this one plus this one plus 1 carry from here, 1 carry for here. So total 4 is available. Is this a diagram logical to you all? Have you explained, understood how this is being drawn out here?
Yes, and how to name the stages here?
No, you don't have to name the stages. Okay, so in the segment, he has just drawn this and then finally made the hardware. So it says ki, the hardware diagram is not shown here. So so you can probably see for each stage 1 row of adders will be required. Okay, so this is shown like this, 4 to 4. So 5 to 4. So you can assume in the first stage. Okay, in the first stage 1, 2, 3, 4, 5. These many adders will be required, right? And the second stage, these many will be required. Because it is 5 into 5, so there will be 1 additional stage. Here we got it for 1 to 3rd stage, right? So for 5 into 5, you will require 1 additional stage. Okay. So for each in each stage, the number of adders that will be required. So you can draw it yourself and try. Okay. So this I drew it only one example for you all, but you can try it out for other multipliers. Okay. You can follow this textbook. So it's a good textbook in few chapters, and where is that? Kareem Abbas. Okay. So handbook of digital CMOS technology. So you can follow that. So he is made for 5 into 5 multiplier, and then he has shown it for 6 into 6 multiplier also. Okay. So here also the same logic. So I guess I'll share these slides and expect you to just try this and make the hardware also out of it. Okay. In case there is any doubts, you can mail it to me, or better is you can put it in the Teams, so that everybody can have a look about the if there are some further discussions required on this subject, we can do that. Okay. So this is for 7 into 6 multiplier. Okay. So the same rule is being followed. Okay, so the set of rules is given here, these rules. Okay, so you need to use that particular rules so that you can use the optimum number of full adders and half adders. Yeah, tell me.
So just explain this part of the slide, slide number 15, where so from second stage to third stage, where we are combining one full adder to another half adder. The first, second, third stage. So how we are just, because it has been converted into one full adder after this. Although we are in the previous stage, we are having one full adder and one half adder. So there must be two carry should be generated.
So let's try and do this particular so that it becomes clear. Okay, this is coming here. I guess there is no issue. This is come here. There is no issue, right? These two, the sum is coming here. Okay, this is coming here, correct? Now there is a carry from here that is going to the next stage. Now there are 3 out here, so that sum is available here from here, right? This one dot which was available previously, that chap is remaining here, and this carry which is coming from this chap, he is coming here. Is it okay till here?
Yes.
Okay. Now here in the next stage, I have put a full adder here. So the sum out here is here, right? And from here also there is one sum which is here, right? And this one I don't have to bother, but there is a carry which is going to come from here, that is available here. Is it okay till here? Till this
yes,
stage?
Sir, but what about this carry being generated from this full adder?
This one, right? On top.
Yes.
That will be taken care of to the next stage. Now here there were 3, so that has got into one single sum, and there is one full adder and one half adder. So 2 carries are expected. So these are the 2 which are going there, and there was one dot available freely here. So that chap also is available here. Is it okay?
Yes.
Correct? Right? And now here there are 3, so there is one sum out here, right? And there is nothing left here, but in the previous stage there was 1, so that carry is coming here. Now here there are 2, but there is 1 here, so that carry is coming here. So I am putting a full adder. So you can do that and try it out for 6 into 6 and 7 into 6 also. Okay, so as
what was the difference between 5 by 5?
5 by 5 and 6
from
by
stage 4 to 5.
So no additional stage is required, but the number of adders is different. If you see here.
Okay. And is there any formula to compute number of stage based on
no.
x by x?
I'm not sure, but probably you can figure it out if something of that can be done. I think as you keep 6 by 6 and 5 by 6 will be same, then it will only increase when you go to 7 to 6 like that, right? You can try to figure out, and maybe you can refer this book if he is given some for the number of stages. Okay. Now there is one more. This is another Dadda. He is second chap who actually proposed a modification of the Wallace tree. Okay, so this is not something very new, but a small modification which turns out to be that it is slightly better. So what he has done, when he says when we have to compress, okay, so first we write as it is like this. Okay, we make the basic Wallace tree, and then we have to suppose initial here this is the Wallace tree where I have maximum here available height, column height is 1, 2, 3, 4, 5, 6, 7, 8, right? So it is so I have to compress this, and how to compress it? He has given a formula that if it is n into m a multiplier, we choose d which is less than the smaller of n and m. Like if you are doing 4 into 4 multiplication. Okay, that means D has to be less than, so 3, minimum 3 it has to be. If you are doing 8 into 8, D has to be 6 and not 7. Why not 7 is because he has suggested the values of D. Okay, this is the series which he has given for optimization. 2, 3, 4, 6, 7, 9, 13, 19, 28 like this. Okay, so you have to keep reducing the column height. Okay, targeting these figures. Okay, now it might appear little vague here. Let's take an example, then things will become clear. Like this is an 8 to 8. Okay. Okay, this is an 8 to 8 multiplier. Okay, so here, 8 into 8 means what the minimum height requirement is 6 from this table, right? 8 into 8 minimum is like smaller of 8 into 8 is 7, right? Minimum of these two 7, less than that 7, but 7 is not permitted. So I have to target height as 6. Okay, now here this is 6, D is equal to 6. Now if you see here there is only 1 element, 2 element, 3 element, 4 element, 5 element. Okay, this is 6 element. Okay, so till 6 element I don't do anything initially. Here I have 7 element. So my target is to bring it to 6 element. So I am just using one half adder. I am not even using a full adder because my target is now 6. I am using a half adder. Here there is one more additional here. So I am using a half adder and full adder. So 1, 2, 3, right? And here there is one carry which is expected. Okay, so finally this will give me 6, right? 1, 2, 3, 4, 5, some here, and one carry which will come from here. So that will make it 6, right? This column height after this operation, will it make 6? Isn't it? Yeah, Rajesh, Rekha, is it okay?
Yes, yes.
How I am making?
So this additional stage is
so
needed.
See,
Okay.
once I do this operation, the column height should be 6 or below. Okay, so I don't try to optimize it, going beyond, trying to bring it below 6. Okay, I'll just target 6. Bare minimum requirement I have to target. Here also, this 3 will become 1 sum. Okay, carry will obviously go to the next stage. This will become again 1. So 1 plus 1, 2, 3, 4, and there will be 2 carries coming from these 2 blocks. So that will make it 6. Okay, and here also that is 1, 2, 3, 4, 5, 6. Okay, but then I have to cater for these 2 delays which are carries which are going to come here. So I have to reduce 2. So that is why I have put a full adder here. So in the first stage, there are only these many things which I will do in the first stage of computation. Okay, first level, I will just use 3 full adders and 3 half adders. Okay, so D is equal to 6. After D is equal to 6, okay, then next I will go to, from this, okay, D is equal to 6. Next is D equal to 4 out here, right? So D is equal to 4, right? Now this is 1, this is 2, this is 3, this is 4. I don't do anything. This is 5. So I put an half adder out here, right? Now this is 1, 2, 3, 4, 5, 6 plus 1 half adder which is going to come here. It will make it 7. So I have to make it 4. So I put an 2 full adders out here. So this will here, right? So this will give me 1, this will give me 1, this is 1 which is already there, one carry which is going to come from here. So that will make it 4. So I progress it like this. Is it okay how this is done? Is it okay with all of you? Yeah. Now from here again I go back, refer to the table. After 4, what is the thing? 3. Okay. Then again here also I will do the optimization so that 3. Then I get 2 and then I get this final. And final in this block only 2 are there. So I use a fast adder. So this is another way of optimization. Okay. So this is slightly better than the Wallace tree. Okay, so But if you see here, for 8 into 8 bit, there will be 1, 2, 3, 4 stages and one a full adder stage which will be required. Okay. So that is one way of doing it. So this is known as Dadda multiplication. Now this we saw in the last semester, a Booth multiplication. So this is an sequential multiplier, right? So what is being done here? If it is an I am multiplying B with A. If it is an 0 out here, this is all 0, and then I am moving the next one towards the left, or I can say this I am moving towards the right, okay, after each operation. So either way, instead of moving this towards the left, I am trying to move these towards the right and keep adding. Again, this is 0, so I am writing all zeros and adding. Whenever this is 1, I am replicating this B as it is out here, right? So this is 1, I am replicating it. Again, there is a 0, then I am putting all zeros here. If it is a 1 out here, then I am putting B as it is. But what I am doing is, if it is a 0, I am going to add same thing, and if it is a 1, I am going to add this. And every time before adding, I am just moving. I am doing one shift right operation. So I keep continuously adding it, and finally I get the product. So this can be implemented by using a Booth algorithm. So what you require out here is, now this B, okay, this data whatever is we are calling is B, okay, that is being fed here as a multiplicand. Okay, this A which we are seeing for this 1 bit, 1 bit, 1 bit, each time we are taking 1 bit, right? That we are going to put it here, and we are going to take the LSB from here, and then we are going to keep shifting it and keep monitoring what is that. Okay, so depending on, if it is 0, then I am going to add this data as it is. If it is 0, I am going to add 0. If it is 1, I am going to add B. So this B. So this B is put here, right, and 0. Now depending on first bit of A is taken. If it is 0, I am going to add 0 to add. If it is 1, I am going to add multiple. So initially this register is also has to be initialized to 0. So B is to be put here. So what is right? So A is to be put here, B is to be put here as per this, right? A is being put here, B is being put here. So this is an n-bit adder. So obviously this will generate a carry also. So even that carry needs to be. So with every clock cycle, okay, so it will this data, the next, as it is we are doing a shift right operation. So slowly first we are seeing this, then we are going to see this, then we are going to see this, then we are going to check whether it is 0 or 1. So whether if it is 0, we are going to add 0. If it is 1, we are going to add B. Okay, so that is what this does. And with every, we have to do a shift operation, and then we have to do an add operation. So every clock cycle you need to do 2 operations, one shift operation and one add operation. And total number of bits here is how many bits are there, those many clock cycles will be required. So that is what is being done here. Okay, so the advantage of this particular circuit is first of all, it requires very less hardware as compared to any multiplier. If you see here, this is just an n-bit adder. So if it is an 64-bit adder, just one 64-bit adder is good enough. Okay, and these are just registers. Okay, this is one 64-bit register, 64-bit register, 64-bit register. Only thing is you require a clock which is fast. Okay, correct. So for modern day processors which is operating in gigahertz, so this is fine enough. Okay, so the entire result will be available in gigahertz is what, in few nanoseconds. So in few nanoseconds this will complete the. So in earlier days when the clock speed was very slow in megahertz, in those days you used these kind of multipliers and all. But now with clock touching gigahertz range, so this is a very good option available. Okay, so it will just take 64 clock cycles, but the total obviously the power requirement is also, because not only so lesser number of each of these are going to consume power also, right? So all those power area, so there is a lot of saving in power and area. So only thing is it requires those many clock cycles. Okay. Now if you talk about this particular structure, then your clock has to be slow because it has to cater for so much of delay. But here what is the delay which requires to be catered for by the clock? What is the block which is likely to give max delay? Anybody?
Adder.
Yeah, this just one bit, like n bit adder. Okay. Here there are several stages of adders which has to be taken care of. Here just a single this requires to be taken care of. Okay. So this is one example where we are multiplying 3 into 5, right? So what we are telling is this data. See, this data needs to be loaded into the register, and also it is to be shifted towards the right. Okay. So let's we can do either way, but let's assume that during the positive edge of the clock, new data will be written into this register, and during the negative edge of the clock, it will be shifted, right? So you can do that. There is no issue with that. So we learnt about mux based registers in the shift registers, universal registers in the last class. So we can use those kind of registers to do this particular operation. So during the if you see here, m remains constant throughout out here, because this is b. Okay. So whether this requires to be added or 0 requires to be added, that will be decided by the last bit. But this particular register continuously holds the same data. Whereas this particular, initially it is updated with the multiplier, but subsequently every shift operation this will keep shifting, right? And only the accumulator gets updated with the add operation. During load, only this register never gets affected. This register gets affected during load operation. During shift operation, this entire thing gets affected. Okay, so that needs to be remembered. So here m never gets affected. So initially a is 0, and I have given q out here. So now q is 1 out here. So that means if it is 1, you need to add. So m gets added to a. So now from m to a you get this, right, during the positive edge of the clock. And then I have q as it is. So q doesn't get affected during load operation. Then again after that, immediately after that, you have to do a shift operation. So when I do shift operation, again m doesn't get affected here. So one from here will come here. Okay, so this a q together they will form the product register. So from a this will go from here during the shift operation. This one comes here. This one gets thrown out. Okay, because we have already taken the decision of what to do based on this one. So now that one is of no more, not used to us, right? Once we have taken this decision, once we have derived this, there is no requirement of 0. So same thing is done. This one is thrown away, and I have 0 here. Now it is 0 out here, and since it is 0, I am going to add 0. So this data of the accumulator is not going to change. It is going to remain as it is. Okay, but shift operation, again it is going to shift. So now this one also. Now here it is a logical shift. Okay, please understand this. Now because in the next modified Booth algorithm, it is going to be an arithmetic shift. Here it is going to be logical shift in these things. So so it is 0 0 0. So when I say logical shift, what is being put here is 0. So this is load, and then there is a shift operation. Now I have 1 here. Again I am adding these two data. Again I have 1 here. So again I am doing a shift operation, and then I have a 0 here. So I am not. So this is a is going as it is to the bottom. So this we did in the VLSI class. So anybody has got a doubt in how to do this, right? I think most of you have done well in the exam also. So this is okay. Now this Booth algorithm, this what we talked about, okay, and this diagram is good enough only for unsigned multiplication. Okay, so this algorithm gets a bit modified when we are talking about signed multiplication. When I say signed multiplication, then this 1 0 1 1 indicates -5 here, right? This is 4, this is -5 in 2's complement. Okay, so this becomes -5 here, right? So in that case, this Booth algorithm is slightly modified, where instead of now I have a q q minus 1. Okay, so initially this is also put 0, q is put here. So I compare this is this same again. Rest of the things are common. This is m, this is a 0 initially. This is q which is put here. Q minus 1. This is additional register which is put here, right? This is 0 out here, right? And this is one more register, right? Here, if I go here, there is one more register, one more bit D flip flop which is put here, not register, one bit D, which is known, which is termed here as Q minus 1 out here. That is also initialized to 0 initially, right? Now, if you see here 0 0, okay, so now I am going to make a decision based on Q0 and Q minus 1, right? Now there are if it is 0 0 or 1 1, I am not going to do anything. Okay, I'm just going to move forward, do the shift operation. But if it is 0 1, then I am going to do a plus 1, and if it is 1 0, I am going to do a minus m. Okay, so that is the difference now. So now the entire algorithm slightly changes. Okay, now it is 0 out here, 0 here. So I am not going to do anything. So a remains as it is. It comes down. And this is also going to come as it is. This is also going. So no operation, right? So no operation is there. Then I am going to do shift operation. In the shift again, m doesn't get affected. This is 0 0 0. It doesn't get affected. 1 0 is going to come from here. This 1 is going to move towards the right. Okay. This 0 0. Again 0 0. It is 0 0. So I am not going to do anything about it in the next. So load operation also, this is going to remain as it is. Again I am going to do a shift operation during the negative edge of the clock. So this is 0. Now this 1 has come here. This 0 has got pushed here. This has got pushed out. So 1 0. Okay. Now 1 0, if you see here 1 0, I have to do a minus m. Okay. A, this is this was a. Okay. M was 1 0 1 1. Right. 1 0 1 1. So 2's complement of 1 0 1 1, what it be? I have written it here somewhere. No, right? So a minus m, right? So this minus this you have to do, right? So you have to do a minus of this first, and then add it to this, right? Add it to 0 0. So if I do if I take 2's complement of 1 0 1 1, will it come 0 1 0 1? Let's try that.
Yes, 0 1 0.
Right? Because I am doing
Yes.
a minus 1. A is this, right? M is this. Okay. So 0 1 0 0, and then add one more 1. So this becomes 0 1 0 1. Right? 0 1 0 1. Right? A minus 1. So is it clear? So you have to be very careful, right? So this is a negative number, but when I am doing a minus 1, so this again you have to make a 2's complement of it. So this comes like this, right? So this is just following. Now after that, once having loaded that, I do one shift operation. Now once I do shift, again this 1 0 1 0, this 1 is pushed here, this 1 goes to the next out here, right here. So I have this now. Now I have 0 1, and now 0 1 says it has to do a plus m, right? So this is a negative number, but I have to just do a plus 1. So I am adding these two, right? I'm just adding 2 and right here. When I'm adding, if it is generating an carry, neglect it. That's what we do in 2's complement. So remember that whenever you are doing such problems, when you are adding these numbers, and if it is generating a carry, just neglect that. Okay, you just have to write the sum out here. So you are writing the sum out here, and then you are doing a shift operation. Now, another important thing which you need to remember out here, the final answer is this. Okay, it is not there in q minus 1. So this is the final answer which is there available. Okay, not this register. So 4 into 4 will give an 8-bit answer which will be available out here. Okay, So now if you see here, I am doing a 4 into minus 5, I should be getting a minus 20 out here. So does this correspond to minus 20? So you can take an 2's complement of it, right? 2's complement of 20, yeah. I am getting this. Okay. Yeah, tell me.
Sir, this q minus 1, can you please once again explain the significance and how we are just putting the value in q minus 1 column?
See, initially there is going to be a register here, q minus 1, which will be preloaded to 0. This will be preloaded to 0. Right? Yes. This will also be preloaded to 0. After that, it is just a shift operations. And I am taking these two from here and here to make a decision. Okay? Is it okay?
So basically in the previous in the previous slide, we were just shifting it through this shift register only.
Correct.
But here in the advanced Booth algorithm, where we are taking the negative numbers and taking the 2's complement of it. So q minus 1, I'm just not able to understand that why. So in the next slides, if you can just please go to the next slide. Yes, this q minus 1 column, this 0 and 1, how we are just putting these values, just not able to understand.
No, as per the Booth algorithm, if it is 0, 0 or 0, 1, we just do an arithmetic shift, right? So yes. Now, this along this is going to be, this has to be an adder subtractor now, right? This has to be an adder subtractor. So one control line for this, whether to add or subtract, also has to come from here. Okay. And if it also what is to be added and subtracted, that is going to come either from here or 0 also. For 1 1 and 0 0, 0 will be added or subtracted. So that input also has to come from here. Okay. So 2 bits of information will come into the control sequencer, right? That will generate 2 control signals. One to select the mux and the second to tell the adder whether to subtract it or to add it.
Right.
Okay.
Thank you.
So that gets modified that way. So so I think one example I have given. I have given one more example of 4 into minus 5 also. Okay. So here it is 4 into minus 5. I think. Is it the same thing? I wanted to give a second example, or I have erroneously pasted the same thing out here, both the cases, I guess. Okay, but you can try out so that you don't make mistakes in the exam. So you can take some number. Okay, now the only thing is, see, this is a 4-bit numbers which we are considering here. So what would be the maximum range in 2's complement? It will be from plus 7 to minus 8, isn't it? Okay, because this gets reserved for sign bit. Okay, so take any number within this range. Okay, only then this logic. Otherwise, if you are considering, say, 8 into some other figure, okay, and then considering it as a sign bit also, then you may not get the desired result. You will get some result, but it may not fit into your logic. Okay, so consider these figures within this range. You can take one odd example and try to do this. Okay, so you will find that this algorithm works fine. So this is a modified Booth algorithm which takes care of the sign multiplication also. Okay.
So here every shift operation is arithmetic shift.
Yes, that is also important. Okay, it is not a logical shift operation, it is an arithmetic shift operation. Okay, when I say, let me see where I have done a shift operation. Here I am making a shift operation, so 0 is being inserted out here, right? Here again I am making a shift operation. If you see here, it is not a 0, which is 1 which is being pumped in here, right? So this is a arithmetic shift operation. So you have got to take care of that as thing also. Is it okay?
Okay, sir.